The last time a comet from this particular family passed this close to the Sun, people reported seeing a second sun in the afternoon sky. That was the Great Comet of 1882. Before that, the Great Comet of 1843. Every member of this family has produced something unforgettable. And now, in April 2026, the newest confirmed member of that family, Comet C/2026A1, discovered just weeks ago in Chile, is heading for a corona passage that makes its ancestors look like dress rehearsals. The optimistic outcome is the most brilliant comet in over a century. The other outcome is something quieter, darker, and considerably more disruptive. Settle in. By the end of this, you will understand why the silence around this story is the strangest part of all. Subscribe and follow along, because what is falling toward the Sun right now is only the opening act. The solar cycle remains locked in its overperforming state. The corona is threaded with magnetic structures already stressed beyond early forecasts, and the conveyor belt of ancient Kreutz fragments continues arriving on schedules written before human civilization existed. Something is racing toward the Sun right now, and almost no one is talking about it. On January 13th, 2026, a team of astronomers operating out of Chile's Atacama desert pointed their instruments at a patch of sky most people will never think about, and they found it. A frozen traveler from the outermost edge of the solar system, already glowing faintly in the darkness, already developing a tail. They gave it the official designation, Comet C/2026A1. The discovery team is called MAPS, the Moving Object and Astronomical Phenomena Survey. And what they found that night in the Atacama was not just another piece of debris drifting through the void. What they found was a comet on one of the most extreme trajectories any object has ever been confirmed to travel in recorded human history. Now, when astronomers talk about comets getting close to the Sun, they usually mean something like a few million kilometers. Comet Halley, the one your grandparents might have seen, passes no closer than about 87 million kilometers from the Sun at Perihelion. That is what most people picture when they hear the word Sungrazer. They picture something distant, safe, beautiful, a smear of light in a dark sky, maybe a news article with a photograph, maybe a backyard telescope moment on a cool autumn evening. That is the comfortable version of this story. Comet C/2026. A1 is not that story. This comet belongs to a family called the Kreutz Sungrazers, and that name alone should make you sit up a little straighter, because the Kreutz family is responsible for some of the most spectacular and terrifying comet events in recorded history. The Great Comet of 1843. The Great Comet of 1882. Comet Ejection Seki in 1965, which was visible in broad daylight and reportedly bright enough to cast shadows. All of them Kreutz Sungrazers. All of them sharing the same orbital lineage, like fragments of a colossal ancestor comet that was torn apart thousands of years ago, its pieces condemned to return to the scene of the crime, one by one, over the centuries. C/2026. A1 is one of those pieces, and it is heading home. Here is what makes this particular object unusual, even by the extreme standards of its family. It was detected farther from the Sun than any Kreutz Sungrazer previously observed. That matters because detection distance correlates loosely with size. The farther out you can see a comet, the more material it is probably throwing off, and the more material it is throwing off, the larger the nucleus is likely to be. As of mid-February, the comet's brightness had already reached magnitude 13.6 to 14 on photometry measurements taken by charge-coupled device cameras. That sounds like a number. Here is what that number means in plain language. Professional equipment is required to see it right now, but it is already bright enough to track, already bright enough to study, and it is getting brighter every single day as it accelerates inward toward the Sun. The comet is also doing something that researchers find compelling and slightly unnerving. It is emitting a turquoise glow. That color comes from a molecule called C2, dicarbon, and it is a strong indicator that the comet is actively vaporizing volatile compounds, ices that have been frozen since the formation of the solar system 4.6 billion years ago. This is a chemically active object. It is alive in the only way that a comet can be alive. It is shedding itself into space as it falls, and it is falling fast. On April 4th, 2026, at approximately 1400 Coordinated Universal Time, Comet C/2026 A1 will reach Perihelion, the closest point in its orbit to the Sun. The perihelion distance is estimated between 0.005 and 0.01 astronomical units. Let me translate that into something your nervous system can understand. 1 astronomical unit is the average distance between the Earth and the Sun, roughly 150 million kilometers. 0.005 astronomical units is approximately 748,000 kilometers from the center of the Sun. 0.01 is about 1.5 million kilometers. The solar radius, the actual physical surface of the Sun, is approximately 696,000 kilometers from its center. So even at the most conservative end of the current orbital estimate, this comet will pass inside a distance of roughly 1.5 million kilometers from the solar surface. At the lower bound of the estimate, it passes approximately 160,000 kilometers above the photosphere. 160,000 kilometers. That is less than half the diameter of Jupiter. It will be traveling through the Sun's corona, the outermost layer of the solar atmosphere, a region where temperatures reach 1 to 3 million degrees Celsius. A region threaded with magnetic field lines carrying forces many orders of magnitude beyond anything we deal with on Earth's surface. A region where the rules of physics operate on scales that are almost impossible to internalize. And if you go to NASA's Jet Propulsion Laboratory website right now and pull up their 3-dimensional orbit viewer for this comet, you will see something that stops the breath. The orbital path line appears to intersect the solar body itself. Now, to be fair, visualization artifacts are common in these tools. The Sun is rendered at a simplified scale in some views, and a line crossing the rendered circle does not constitute an official confirmation of physical impact. No official NASA statement has confirmed that this comet will strike the Sun. That has to be said clearly and honestly. But the trajectory is real. The corona crossing is real. The physics of what happens when a several kilometer wide ball of primordial ice and dust plunges into a magnetized plasma at several hundred kilometers per second. That is real, and it is worth thinking about. There are 3 broad outcomes on the table. The comet survives perihelion largely intact, emerges on the other side, and becomes one of the brightest comets in over a century, possibly visible in daylight, possibly visible to the naked eye for weeks. That is the optimistic scenario, and honestly, it is a beautiful one. The second outcome is that the comet disintegrates before or during perihelion, as many sungrazers do, leaving behind a trail of dust and gas that fades quietly into the solar wind. Anticlimactic, but not dangerous. The third outcome is the one that has a small but serious scientific community watching very carefully right now. The one that has barely registered in mainstream English language media. The one that prompted the making of this documentary. In that third scenario, the comet's plasma injection into the Sun's corona interacts with pre-existing magnetic structures in a way that triggers or accelerates a major magnetic eruption, a coronal mass ejection. A billion-ton cloud of magnetized plasma launched from the surface of the Sun at several million kilometers per hour. We have always believed that the Sun ignores everything that touches it. But what if, under the right conditions, it doesn't? What happens when a frozen mountain of primordial ice dives into a star already on edge? If that sounds dramatic, wait until we revisit a moment from 2011 that the scientific establishment called a coincidence, and that some researchers have never quite been able to stop thinking about. Most people have never heard of the Sungrazer that fell into the Sun on October 1st, 2011. It was observed through the Solar and Heliospheric Observatory Satellite, SOHO, a spacecraft that has been watching the Sun continuously since 1995. The comet was small, likely a fragment from the same Kreutz family lineage, and it plunged into the corona on a Tuesday morning, briefly brightening as it vaporized, and then it was gone. No fireworks, no visible explosion on the solar surface, just a streak of light on an instrument feed, watched by a relatively small community of solar physicists and comet enthusiasts, and then forgotten. Except for one thing. In the hours following the comet's disappearance, a coronal mass ejection erupted from the Sun's near side. A real one. A measurable, significant release of solar plasma that propagated through the inner solar system. And some researchers noticed the timing. Now, the official scientific consensus is important to state clearly here, because this documentary is not interested in misleading you. The mainstream position in solar physics is that coronal mass ejections arise from internal magnetic reconnection processes within the Sun itself. They are driven by the buildup and sudden release of magnetic energy stored in complex field configurations near active regions. The mass of a comet, even a large one, is negligible compared to the mass of solar plasma. A comet striking the Sun is, from a purely gravitational standpoint, roughly equivalent to a mosquito landing on a freight train. The Sun does not register it. That is the established view, and it is supported by extensive modeling and decades of observation. But plasma physics is not only about mass, it is about electromagnetic interaction. And this is where the conversation gets more complicated and more interesting. As a comet approaches the Sun, something remarkable happens to it. The heat begins to strip away the outer layers of ice and dust, releasing gases that immediately become ionized by ultraviolet radiation. The comet develops a plasma tail, a stream of charged particles that is pushed directly away from the Sun by the solar wind. That tail is not just aesthetic, it is a channel of ionized material connecting the comet to the broader electromagnetic environment of the corona. The coronal magnetic field, in the region a Sungrazer passes through, can reach between 1,000 and 5,000 Gauss in the vicinity of coronal loops, those arching structures of magnetized plasma that you have probably seen in images of solar eclipses, towering above the surface like bridges built by something that does not understand moderation. The electromagnetic forces in those structures are, depending on how you measure, somewhere in the range of 10 to the 36th power stronger than gravitational forces at the same scale. In other words, the physics of this interaction is dominated not by how heavy the comet is, but by how it moves through a field. The theoretical question, and it remains theoretical, with no verified experimental confirmation, is whether a sustained injection of ionized plasma along a specific trajectory could act as a perturbation to an already stressed magnetic flux rope. A magnetic flux rope is a bundle of field lines wound around each other like a twisted cable, and in solar physics, they are understood to be the primary structures involved in coronal mass ejection launch. They store enormous amounts of energy. When they become unstable, they erupt. The question that a small but credentialed subset of researchers has quietly asked is whether an external plasma event, a comet's ionized trail threading through a coronal loop region at the right moment, could provide the perturbation that tips an already unstable flux rope into eruption. Not cause the CME from scratch, not overpower the Sun's internal dynamics, but nudge, accelerate, trigger what was already close to triggering. No peer-reviewed paper has confirmed this mechanism for the 2011 event. The temporal correlation between the comet and the subsequent CME has been noted and subsequently attributed to coincidence by the majority of the research community. But the 2011 Sungrazer was small. It was a fragment. It was not Comet Lovejoy, which arrived in December of 2011 and became a genuine spectacle, surviving perihelion in a way that stunned astronomers, briefly becoming visible to the naked eye from the southern hemisphere. And C/2026, A1 may be significantly larger than Lovejoy. It was detected earlier, suggesting a more active nucleus, producing more volatile compounds. It has a developing tail at a distance, where many sungrazers are still invisible. If size correlates with the scale of plasma interaction with the corona, and there is reason to think it might, then comparing C/2026 A1 to the 2011 fragment is like comparing a stone thrown in a pond to a boulder. The pond is not going to notice the stone. But nobody has done the experiment with the boulder yet. And while we are sitting here wondering about the physics of plasma interactions in a star's outer atmosphere, a much simpler question is waiting in the wings. If a CME did occur, large, fast, and pointed in the wrong direction, how bad could it actually be? Because we have a historical data point on that question, and the answer is not comfortable. History is full of things we noticed and then decided not to think too hard about. The Kreutz Sungrazer family has been writing its signature across the sky for thousands of years, and the pattern it has left behind is one of the most dramatic in all of observational astronomy. The Great Comet of 1843 became so bright that it was visible in broad daylight on March 29th of that year. Observers reported seeing it near the sun in the afternoon sky, a thing that should not exist, a light where no light should be. The Great Comet of 1882 was described by sailors at sea as a second sun. It passed so close to the solar surface that it was observed moving through the corona by telescopes, and it survived. Comet Secchi in 1965 reached an estimated magnitude of -10 to -11 at perihelion. For comparison, Venus at its brightest is around -4.6, making it potentially the brightest comet in 1,000 years. People watched it pass within 460,000 kilometers of the solar surface in the middle of the day. And Comet Lovejoy in 2011, the one mentioned in the previous chapter, not only survived a corona passage that most models predicted would destroy it, but emerged visibly intact, developing a brilliant tail visible from the International Space Station. All of these objects share an orbital heritage. They are fragments of a progenitor comet that almost certainly exceeded 100 kilometers in diameter before it was torn apart, probably during a previous close solar passage, possibly thousands of years ago. Each surviving fragment follows a slightly different orbital path, different periods, different orientations, but they all converge at the same fatal point, the inner corona of the sun, and they all carry the potential to produce something unforgettable. C/2026. A1 fits this lineage precisely. Its retrograde orbital inclination, measured at approximately 140 to 144 degrees, is characteristic of the Kreutz family. Its orbital geometry, its velocity at perihelion, which will reach several hundred kilometers per second, and its detection history all point to membership in this ancient fragmented clan. What is not yet known with certainty is the size of the nucleus. Direct imaging of comet nuclei from Earth is extremely difficult, particularly at this distance, but the comet's early activity and brightness development suggest a nucleus that is potentially larger than many previously observed Kreutz members. Early detection distance does not perfectly predict nucleus size. There are comets that outgas prolifically from a small nucleus, and comets that are large but chemically inert. But the combination of detection distance and outgassing activity here has caught the attention of researchers who track this family for a living. If the nucleus is large enough to survive the corona passage, and Lovejoy demonstrated that survival is possible even under extreme thermal and tidal stress, the brightness projections are astonishing. Conservative estimates place peak magnitude around -4, which is similar to Venus at its maximum, and would make the comet visible in twilight or dawn skies with the naked eye. More optimistic estimates, depending on dust production and the geometry of forward scattering, a phenomenon where comet dust aligned between the Earth and Sun can amplify apparent brightness dramatically, push potential peak magnitude to -7 or even -7.5. That would make C/2026A one the brightest comet in over a century, and potentially the most spectacular natural sky event of this generation. But here is the complication, and it is worth pausing on. Fragmentation during or before perihelion is not a failure scenario for the comet's visual performance. It is actually a potential enhancement. When a comet breaks apart under tidal stress or thermal shock, it exposes fresh interior material to solar radiation, dramatically increasing outgassing and dust production. The total surface area of the coma increases. The tail can broaden and brighten even as the nucleus disintegrates. Several historically notable comets, including portions of the 1882 event, showed this behavior. So the comet breaking up does not necessarily mean the show ends. It might mean the show multiplies. The question that sits at the uneasy intersection of cometary science and solar physics is this. If fragmentation occurs within the coronal magnetic flux rope region, if multiple fragments, trailing their individual plasma tails, thread through stressed magnetic structures simultaneously, could the electromagnetic perturbation be more complex than a single body would produce? Could multiple simultaneous plasma injections into the corona create a more chaotic interaction with pre-existing magnetic configurations? This is speculative. There is no verified evidence confirming this scenario. No published model has been run on multi-fragment corona interaction at this scale. But it is a question that a comet of this potential size and this orbital trajectory makes worth asking, because the alternative, assuming the physics of this event are identical to every previous smaller event, may be precisely the kind of assumption that gets us surprised. And if that scenario did happen, if the sun responded to this visitation with something large and sudden, the Earth would care. The Earth would care enormously. Because we have seen, once in recorded history, what the sun can do when it is angry. And we have spent the 167 years since then building a civilization that would not survive a repeat performance nearly as well as the telegraph operators of 1859. On September 1st, 1859, a British astronomer named Richard Carrington was doing something that sounds almost quaint by modern standards. He was sketching sunspots. He was sitting at his telescope in his private observatory, drawing what he saw, when a white light flare erupted from the solar surface, the first solar flare ever directly observed by a human being. He watched it brighten and fade in about 5 minutes. He made a note. He told his colleagues. They were politely interested. And then, approximately 17 hours and 40 minutes later, the largest geomagnetic storm in recorded history arrived at Earth. The auroras were visible from Cuba, from Hawaii, from Rome. Telegraph systems across North America and Europe went haywire. Some lines sparked even when operators disconnected the batteries, driven entirely by the induced electromagnetic current from the storm. Telegraph offices caught fire. Messages could not be sent. The global communications infrastructure of 1859, primitive as it was effectively paralyzed for days. Now, imagine that event happening tomorrow. Lloyd's of London, not an organization known for catastrophism. They are known for pricing risk, which is a very different and more ruthless discipline. Published a study in 2013 that estimated the economic cost of a Carrington-scale geomagnetic storm striking modern infrastructure at between 0.6 and 2.6 trillion US dollars. Those numbers are from over a decade ago. The digital infrastructure they were assessing has expanded enormously since then, and the estimate has not been updated to reflect the satellite constellations, the cloud data centers, the GPS-dependent logistics networks, the high-frequency trading systems, and the cellular communication arrays that have been added to the global technological fabric in the intervening years. The real number is almost certainly higher. Here is what a major geomagnetic storm actually does to a modern society. High-voltage transformer stations, the large custom-built pieces of equipment that step voltage up and down along power transmission lines, are particularly vulnerable to geomagnetically induced currents. These currents are slow, quasi-DC flows induced in long conductive infrastructure by fluctuations in Earth's magnetic field during a storm. They saturate the cores of large transformers in ways those transformers were not designed to handle, causing overheating, damage, and in severe cases, catastrophic failure. The critical fact about these transformers is that they are not mass-produced items sitting in a warehouse somewhere. They are custom-engineered, often country-specific, built on order, and replacement lead times can range from months to years, depending on the size and specification. A Carrington-level event could damage hundreds of them simultaneously across multiple continents. Replacing them under normal manufacturing conditions might take a decade. GPS timing signals, which most people think of as navigation tools, are actually the invisible synchronization backbone of the modern economy. Financial transaction clearing systems, telecommunications, switching networks, and power grid frequency management all depend on GPS time signals accurate to within nanoseconds. A geomagnetic storm that disrupts satellite operations by inducing drag on low Earth orbit satellites, by disrupting ionospheric propagation, by affecting the electronics aboard GPS satellites directly, would introduce timing errors that cascade through financial and infrastructure systems in ways that are genuinely difficult to model fully. Aviation over polar routes, which are common for transatlantic and transpolar commercial flights, would be grounded immediately due to communications blackout and radiation exposure risk. Now, here is the important scientific caveat that has to sit alongside all of this. The current orbital geometry of C/2026A1 suggests that perihelion occurs on the far side of the Sun relative to Earth. Most coronal mass ejections, even large ones, are not Earth-directed. A CME launched from the far side propagates into the inner solar system in a direction that does not intersect Earth's orbit at the relevant time. NOAA's Space Weather Prediction Center is active, transparent, and actively monitoring solar conditions. No official forecast from any space weather agency currently indicates an imminent Earth-directed CME event. The scenario being described here, a comet-triggered CME that happens to be geometrically aligned with Earth, requires multiple independent factors to align simultaneously, and the probability of that specific combination is low. But here's the question that keeps space weather researchers up at night, the one that does not go away even when the immediate probability is small. Are we hardened enough? Are the critical infrastructure systems that modern life depends on prepared for an event that has a 1 in 100 or 1 in 1,000 year probability of occurring in any given year? And if they are not, and the consensus answer from the engineering and policy community is that broadly they are not, then the question of whether this particular comet on this particular date triggers this particular outcome becomes less important than the deeper question it forces us to confront. We have built our civilization on the assumption that the sun will behave itself. We have insured our houses against fire and flood, but left our entire technological infrastructure exposed to a class of event that we know, with certainty, has happened before and will happen again. So if the risk is real, and the infrastructure exposure is real, and the historical precedent is real, why is nobody talking about it? You would think that a comet on a trajectory this extreme, with implications this significant, would be front-page news. Pull up any major English language news outlet right now and search for Comet C/2026A1. You will find almost nothing. A paragraph in a science blog, perhaps. A thread on an astronomy forum. Some posts on X, the platform formerly known as Twitter, where amateur astronomers and independent content creators have been tracking this object with a combination of genuine expertise and entirely understandable alarm. If you read Japanese, you will find more. Japanese science media has covered this event with notably more thoroughness than its English language counterparts. But in the mainstream Western media ecosystem, the one that reaches hundreds of millions of people who might conceivably want to know that a large icy object is heading for the sun at several hundred kilometers per second, the silence has been close to total. Why? The most generous explanation, and probably the most accurate one, is that comets are notoriously unpredictable, and the media has been burned before. In 2013, Comet Ieson was billed by enthusiastic coverage as a potential comet of the century. It was going to be brighter than the full moon. It was going to be visible for weeks. It was going to be the defining sky event of a generation. On Thanksgiving Day, 2013, Ieson rounded the sun and disintegrated. The comet of the century became, in the span of a few hours, a dispersing cloud of dust. The coverage that had built up expectation had no graceful way to land that disappointment, and the embarrassment left a mark. Editors who were around for Ieson remember it. The institutional reflex to avoid comet hype is understandable, earned, and in most cases entirely rational. The second explanation is that the CME trigger hypothesis, the idea that a comet's corona passage could influence solar magnetic activity, lacks peer-reviewed support robust enough to justify mainstream coverage. Science journalism operates appropriately with a threshold of evidential credibility. A speculative mechanism without confirmed observational validation or published modeling does not clear the bar for a serious outlet running a story under a serious headline. That is how science journalism is supposed to work, and it serves an important function in preventing panic over scenarios that are genuinely unverified. The third explanation is psychological, and it applies not just to journalists, but to all of us. Human beings are profoundly poorly calibrated when it comes to low probability, high consequence risks. We dismiss them. We reclassify them as other people's problems. We defer them to the future. Institutions, which are just collections of human beings with additional organizational incentives, are even worse at this than individuals are, because institutions also have reputational risk calculations running alongside every editorial or policy decision. Publishing a story about a comet that might trigger a CME that might be Earth-directed and might damage the power grid is a story with an enormous number of mites in it, and every single one of those mites is a potential liability if the event does not materialize and the headline is remembered. What this explanation does not require, and this is worth saying directly, is a conspiracy. No evidence exists of coordinated suppression of information about C/2026A1. No official warnings have been withheld. No government agency has classified data about this comet's trajectory. The JPL orbital data is publicly accessible. The discovery announcement was made through standard channels. The absence of mainstream coverage does not constitute a cover-up. It constitutes a predictable collision between an uncertain event, a burned media environment, and human cognitive habits that are not designed to process this category of risk comfortably. But there is a difference between suppression and neglect. And the argument being made here is not that someone is hiding something. The argument is that the combination of factors surrounding this event, the orbital extremity, the comet's size indicators, the solar cycle context, the infrastructure vulnerability, adds up to something that the public has a right to at least be aware of, even if the ultimate probability of a harmful outcome is low. Because awareness is not the same as panic. Information is not the same as crisis. And the people watching this video right now are demonstrating something important. They asked. They sought out information. They are precisely the kind of audience that can handle complexity without collapsing into either denial or hysteria. And while this silence has held in the mainstream, the sun has been doing something that does not require a comet to be alarming all on its own. The sun runs on a cycle. Every 11 years, approximately, Solar magnetic activity rises from a quiet baseline to a peak of intense, complex activity, and then falls back again. These cycles are numbered sequentially, and the one we are currently living through is solar cycle 25. When cycle 25 began around 2019, the official forecast from NOAA and the international solar science community was cautious. Cycle 25 was expected to be similar in strength to cycle 24, which had been a relatively weak and unremarkable cycle. Modest activity, modest peak, nothing too dramatic. The kind of solar cycle that generates academic papers and not much else. The kind that lets infrastructure engineers sleep well. The sun did not get that memo. Solar cycle 25 has significantly exceeded its early forecasts. By 2024 and 2025, the sun was producing X-class flares, the highest classification in the solar flare scale, at a frequency that caught researchers off guard. Not slightly off guard, meaningfully, uncomfortably off guard. The kind of off guard that produces revised forecast documents and quietly updated prediction models that walk back the original confident projections without making too much noise about having been wrong. Sunspot groups have been larger, more magnetically complex, and more energetically active than the early models predicted. The peak of cycle 25 was initially expected around 2025, but updated analysis has pushed the expected maximum into a range that encompasses 2024 through 2026, meaning that April of 2026, the exact month of C/2026 A1's perihelion, falls within a window of genuinely elevated solar activity baseline. The sun is not calm right now. The sun is behaving like a system under internal pressure, producing events on a schedule that has surprised even experienced solar physicists who have spent their careers watching it. And experienced solar physicists are not easily surprised. To be absolutely clear about what this means and what it does not mean, because clarity matters here, solar instability does not require a comet. The sun will produce major flares and coronal mass ejections regardless of what C/2026 A1 does on April 4th. The baseline risk from solar activity in the current part of the cycle exists completely independently of any comet, any trajectory, any astronomical event originating outside the sun itself. That is important to hold on to. This is not a story where a comet is required to make the sun dangerous. The sun is already, by objective measure, more active than it has been in over a decade. It was doing this before anyone in Chile found this comet. It will continue doing this after April 4th, regardless of what happens at perihelion. But here is the thing about context. Context changes the meaning of events without changing the events themselves. What the comet introduces, and this is the speculative layer that has to be labeled honestly and clearly as such, is not a cause, but potentially a perturbation. If the corona is already in a state of elevated magnetic stress due to the solar maximum environment, if active regions are already accumulating energy in flux rope configurations that are approaching instability thresholds on their own internal timeline, then the arrival of a large, chemically active sungrazer trailing a plasma column hundreds of thousands of kilometers long through those structures introduces a variable that was not in the pre-existing system. A perturbation is not the same as a cause. A perturbation is the last straw. It is the specific vibration at the specific frequency that triggers the avalanche that was going to happen anyway. Just perhaps not today, perhaps not in this direction, perhaps not at this magnitude. No verified evidence confirms this interaction mechanism. No published model has demonstrated this specific chain of events at this scale, stating that clearly is not a hedge. It is the scientifically honest position, and this documentary is committed to that position even when it makes the story less tidy. But the combination of an overperforming solar maximum and a historically extreme sungrazer arriving at perihelion on April 4th, 2026, creates a context in which the question deserves to be asked more seriously than it currently is being asked in public forums. The question is not whether the comet will cause a catastrophe. The question is whether we are thinking clearly about the overlapping risk environment that surrounds this event, and whether that overlapping environment has been communicated to the people who live inside it. There is also a structural observation worth making about the nature of solar maximum windows and the statistical probability of major Earth-directed events occurring within them. This is not speculation. This is historical pattern analysis. Statistical review of CME records across multiple solar cycles shows that the probability of a severe geomagnetic storm, one rated G, 4 or G5 on NOAA's scale, meaning widespread voltage control problems, possible grid collapse at high latitudes, satellite surface charging, and degraded GPS operations, increases substantially during the years immediately surrounding solar maximum. The storms cluster around the peak. They always have. The 9 months of 2025 that have already passed included the strongest geomagnetic storm since the early 2000s. A G5 event in May 2024 produced auroras visible from Florida, from Texas, from Spain, from regions where people had never seen the northern lights in their lifetimes, and pulled over on highways to photograph something that felt like it belonged to a different planet. That was a real event. It happened. And by the standards of what solar maximum can produce, it was not the ceiling. It was a demonstration that the ceiling exists and is higher than most people had considered. We are already in elevated territory. April 4th arrives in this context, not in a quiet interlude, not in a solar minimum year when the sun is drowsing and magnetically simple, but in the operational peak of a cycle that has been consistently stronger than the models that were supposed to predict it. The forecasters are not incompetent. Solar cycles are genuinely difficult to predict from their beginnings. The physics of the solar dynamo, the convective, rotating, magnetically self-sustaining engine that drives these cycles, involves nonlinear interactions that resist precise long-range modeling in ways that the atmosphere and ocean, themselves notoriously complex, do not fully prepare you for. Predicting a solar cycle from its start is a little like predicting a hurricane season's total intensity from the water temperature in January. You can make an educated estimate. You will sometimes be wrong in ways that matter. Cycle 25 has been one of those times, and it has been wrong in the direction that carries consequences. Even if April 4th passes without incident, even if the comet disintegrates quietly somewhere in the outer corona, and the sun responds with nothing more than a routine active region flare that gets a brief mention in the weekly NOAA space weather summary, the solar maximum context does not disappear on April 5th. The risk window extends for months beyond any single date on the calendar. The magnetic energy stored in complex active regions does not discharge cleanly and reset on a human schedule. It accumulates. It shifts. It finds the configuration it needs, and then it releases on its own timeline according to physics that does not consult the calendar we have placed around it. April 4th is simply the date when the most unusual external variable enters the equation. It is the date when a several kilometer wide ball of primordial chemistry, moving at several hundred kilometers per second, intersects with a magnetically stressed stellar atmosphere that is already operating above its predicted baseline. Whether that intersection produces anything beyond a spectacular visual event, or no visual event at all if the comet fragments early, is a question that will be answered by the physics, not by the coverage, not by the silence, and not by how prepared or unprepared we are when it happens. And that word, prepared, is the one that lingers. Because the solar maximum of 2024 through 2026 is not occurring against the technological backdrop of 1989, when the Quebec blackout demonstrated what a G5 storm could do to a regional power grid, and the lesson was filed away and largely not acted upon at a systemic level. It is not occurring against the backdrop of 1989's satellite constellation, which was a handful of research and communications assets compared to what currently orbits. It is occurring against the backdrop of the most complex, most GPS-dependent, most electrically interconnected civilization in the history of the species. A civilization that has added, in the years since the last serious policy conversation about space weather hardening, entire new categories of infrastructure whose vulnerability to geomagnetic disturbance has not been fully characterized. That brings us to something that did not exist in 1859, or in 1989, or in any previous episode of severe space weather in the historical record. The new tools we are building to protect what we have built, and the uncomfortable gap between how fast those tools are developing and how fast the exposure they are meant to address is growing. The gap is not closing as quickly as the people who understand both sides of it would like. And the comet falling toward the sun right now is, whatever else it turns out to be, a very well-timed reminder that the gap exists. We are better at watching the sun than we have ever been, and we are more exposed to it than we have ever been at exactly the same time. Both of those things are simultaneously true, and the tension between them is not a paradox. It is a policy failure, dressed up as progress. We have spent the past 3 decades building tools that can see the danger coming, and the past 3 decades building a civilization that is more damaged by the danger than the one that came before it. The monitoring has improved. The vulnerability has outpaced the monitoring. And somewhere in that gap lives the question that April 4th, 2026 is quietly forcing into the open. In the past 3 years, machine learning systems trained on decades of solar magnetogram data have demonstrated a genuinely remarkable ability to identify pre-flare magnetic signatures hours before the flare occurs. These are subtle patterns, subsurface plasma flow signatures, and surface field configurations that human analysts missed for decades, not because they were inattentive or poorly trained, but because the patterns exist across spatial scales and temporal windows too large for unaided human perception to connect reliably. The sun is a big place. The precursor signals are distributed across it in ways that require simultaneous attention to thousands of data points evolving over hours, and the human visual system was not designed for that task. The algorithms were. Machine learning systems do not get tired. They do not shift their attention. They do not have a preferred region of the solar disk that they find more interesting than others. They look at everything, all at once, all the time, and they have found patterns that decades of human observation missed entirely. The results are not perfect. The false positive rate remains a genuine operational challenge. A system that cries wolf too frequently trains the operators who receive its alerts to discount them, which defeats the purpose of having an early warning system in the first place. And the lead time produced by current models is measured in hours, not days. Hours is better than minutes, which is what solar physics offered for most of the 20th century. But it is not enough time to do much beyond alerting grid operators to reduce load and instructing satellite operators to enter safe mode. It is warning time, not preparation time. The field is moving quickly, and the next generation of models, trained on the richer datasets that newer solar observation satellites are producing, may push that lead time further. But right now, in February of 2026, hours is what we have. The National Oceanic and Atmospheric Administration and the European Space Agency are both actively integrating machine learning tools into their operational space weather forecasting pipelines. This is not experimental. This is deployed infrastructure. The NOAA Space Weather Prediction Center in Boulder, Colorado, runs forecasts that update every 30 minutes, 24 hours a day, 7 days a week, 365 days a year. There are people whose entire professional lives are devoted to watching the sun so that the rest of us do not have to. That is worth acknowledging and worth appreciating, because they are good at what they do, and they are doing it with less public recognition and fewer resources than the stakes arguably warrant. At the same time, And this is the other side of the ledger that has to be read alongside the progress. The surface area of human civilization that is exposed to a severe space weather event has expanded in ways that make every previous risk estimate look conservative. The Lloyds of London study from 2013, the one that produced the $0.6 to $2.6 trillion damage figure for a Carrington scale event, was calculated against an infrastructure environment that has since changed dramatically. Since that study was published, the total number of operational objects in low Earth orbit has grown from a few hundred to several thousand, driven primarily by the rapid deployment of broadband internet constellations from companies that did not meaningfully exist when the estimate was calculated. Starlink, OneWeb, Amazon's Kuiper constellation, still in deployment. Each of these satellites operates in an orbital environment that is directly and immediately affected by elevated geomagnetic activity. Atmospheric drag increases during storms as the upper atmosphere expands from heating, causing satellites to lose altitude faster than their onboard propulsion can compensate for at extreme event levels. In February of 2022, a modest geomagnetic storm, modest, not exceptional, not historic, coincided with a Starlink deployment and destroyed or degraded several hundred satellites that had not yet raised to their operational orbits. Several hundred satellites lost in one storm that was not even a major event by historical standards. A Carrington-scale geomagnetic disturbance arriving in the current low Earth orbit environment, which now contains tens of thousands of objects rather than a few hundred, would produce cascading debris and orbital disruption that we do not have a clean model for, because nothing like it has ever happened in an orbit this crowded. The GPS dependency problem has grown deeper and more structurally embedded since 2013 in ways that are easy to underestimate, because GPS has become so invisible. People think of GPS as the thing that tells their phone which street to turn on. That is the least critical use of the technology. The proliferation of autonomous vehicle systems, the integration of GPS-derived precision timing into 5G network synchronization infrastructure, the expansion of drone logistics operations across multiple countries, and the incorporation of GPS timing signals into hospital systems, financial networks, and electrical grid management have all added new load-bearing elements to an architecture that was originally designed for navigation and has been quietly repurposed into the timing backbone of the modern economy. Microsecond precision timing, accuracy to within 1/1,000,000th of a second, now touches the operational logic of systems that most people have never thought about in this context. Hospital medication dispensing schedules that are logged and verified against network timestamps. Electrical grid frequency regulation that uses GPS timing to synchronize phase relationships across interconnected systems spanning thousands of kilometers. Transaction clearing and settlement systems that rely on timestamp verification to establish legal sequence of trades and payments. None of these systems were designed with the assumption that GPS timing could disappear for 12 hours. None of them have been publicly stress tested against that scenario in a way that has produced published results. The global financial system's specific reliance on synchronized timestamp verification is a vulnerability that receives remarkably little public discussion given its systemic importance. During a geomagnetic storm in August of 2023, several regional financial clearing systems in Northern Europe and Canada reported minor timing anomalies. The anomalies were corrected before causing transaction failures. The corrections were made by human operators who recognized the signatures and intervened manually. Minor, corrected, no headlines. But noted in internal incident logs because that is what serious infrastructure organizations do. They note the stress points, they file the reports, and then they continue operating in an environment where the stress points remain. A more severe event would not provide the same comfortable correction window. A Carrington-scale storm does not arrive gently enough for a human operator to notice the anomaly, identify the cause, and manually override the affected system before the cascade begins. All of this is the background radiation of the story, the context that exists regardless of what happens on April 4th, regardless of what C/2026 A1 does or does not do to the Sun's corona. The probability of the worst-case scenario in which a large Kreutz Sungrazer triggers a major CME, that CME happens to be precisely Earth-directed, arrives during an already elevated geomagnetic storm window, and impacts a grid that has not been hardened to the standard the event requires, is low. Every link in that chain has to hold simultaneously, and several of those links are individually improbable. This is not a prediction. This video is not warning you that a blackout is coming on April 5th. What this is, and it is something more uncomfortable than a prediction, is an observation about the architecture of a risk that our civilization has chosen, collectively and largely without explicit public discussion, to leave open. Not because the engineers do not know it is there, not because the policymakers have never been briefed, but because closing it costs money and requires coordination across jurisdictions and industries that have competing short-term incentives, and because the event it protects against might not happen for another 100 years, and because the quiet decades between solar maximum windows have a way of making the whole thing feel theoretical. The comet is brightening. In the Atacama Desert and in observatories from Arizona to Japan, astronomers are watching the magnitude readings climb each week. They are refining the orbital parameters with each new observation arc, narrowing the uncertainty on the perihelion distance, arguing in forum posts and preprint comments about what the brightness curve implies for nucleus size. They are running models they will not publish until after the event, because the professional cost of predicting a catastrophe that does not materialize is real, and the field has Comet Ison's ghost looking over its shoulder at every optimistic projection. The Sun is producing complex active regions on a schedule consistent with a solar maximum that has already exceeded every forecast made for it. The machine learning systems are scanning magnetogram data for the precursor signatures they have been trained to find, updating their probability estimates hourly, flagging regions of interest to human forecasters who then decide what, if anything, to communicate to the grid operators downstream. April 4th, 2026 will answer the immediate question. One date, one outcome, one data point added to the long record of humanity watching the nearest star and trying to understand what it is telling us. But the larger question does not resolve on April 4th. The larger question is not about this comet. It is about a civilization that has built its most critical systems inside the operating radius of something it fully understood was dangerous, and decided, year after year, budget cycle after budget cycle, that hardening those systems could wait. We have always assumed that the infrastructure built in the quiet years between solar events would hold through the events themselves. We have always assumed that someone, somewhere, in some agency or utility or defense department, was making sure the transformers were protected, that the backup timing systems were tested, that the contingency protocols existed in a form that was funded and practiced and ready. We have always assumed, at some quiet foundational level, that the Sun was manageable. It has always been the closest star. It has always been the most powerful object in our part of the galaxy. It has warmed every generation of life that has ever existed on this planet, driven every weather system, powered every living cell in every organism that has ever drawn breath. It gave us everything we have ever had, and it has never once promised not to take it back. The comet is falling. The Sun is burning. April 4th is coming, and we are watching, which is the best we have ever been able to do, and the least we have ever been able to do, at exactly the same time.